Hey guys, today we're going to be talking about inscribed angles and also intercepted arcs, all within circles here. So first off, let's define what an inscribed angle is, and we'll see different cases of them. So an inscribed angle, it's an angle in a circle. So we have a circle here, call it circle A. An inscribed angle is going to be an angle that has a vertex on the circle. So you can have like a vertex here, call it vertex B. So it has a vertex on the angle, and both of the sides of the angle are chords of this circle. So example would look like this. And we'll just use C and D here. So angle DBC, this angle is an inscribed angle. Has the vertex, is a point on the circle, and both of the chords are part of the circle as well. So both the sides are chords of the circle. Now when you have an inscribed angle like this, we also create what we call an intercepted arc. Now an intercepted arc, that's going to be an arc that its endpoints of the arc are going to fall on the sides of an inscribed angle. And here we have the intercepted arc DC. So the arc DC, notice how both the endpoints of that arc fall on the inscribed angle DBC. It also is going to be the arc that is on the interior of the angle. So DC is the arc on the interior. It's that minor arc. It's not the major arc that goes the other direction, the larger one. It's going to be the one that's on the interior of the angle. So DC we would call an intercepted arc here. Now when we have inscribed angles, there's really three possibilities of them. So the first case, say case 1, if you have a circle, circle A again, and you have an inscribed angle, first case is one of your sides of that angle goes through the center of the circle. So the center falls on one of the sides. That's case 1. Case 2 would mean, we'll stick with circle A, would be like if you had an inscribed angle and the center is in the interior of the angle. Notice how the center here is not on one of the sides, but it's in the interior. And that leads us to case 3 with an inscribed angle. Ooh, not my best circle. That would be if you have an inscribed angle. So this is the third type of inscribed angle, where the center is not on the interior, it's on the exterior of that angle. So case 1, you can have an inscribed angle with the center falling on one of the sides. Case 2, the center is going to be in the interior of the angle. And in case 3, the center is in the exterior of the angle. Now today we're going to focus on two main theorems, and we'll do some examples with them. So our first theorem, if you're following along, is page 723 in the book. This is theorem 10.6. It says, if an angle is inscribed in a circle, then the measure of the angle equals half the measure of its intercepted arc. And what that's telling us, I'm going to use the exact example that they have. That was all right. We have this circle with our inscribed angle here. Call this A and B. And we'll call angle 1. So the measure of angle 1 here, your inscribed angle, the measure of angle 1, is going to be half the measure of your arc. So 1/2 the measure of arc AB. Or you can think of it like the measure of arc AB is equal to 2 times the measure of angle 1. The measure of this arc is going to be double the measure of that angle. And we're not going to go through the proof of this. We have to prove all 3 cases because there's 3 cases of an inscribed angle. So we'll just go to a little example problem of how we can use this theorem. So we'll go right in the book with this. There's one example that's worked out, so I won't do that one. That way you can maybe try it on your own and see step for step. So we'll do the guided practice. And with the guided practice one, we have this circle right here. We are given, let's see, I believe this is what we have. we have C, D, E, and F, like this. And then we are told this angle is 40 degrees, and this arc has a measure of 98 degrees. All right, and our goal is to first find the measure, we'll do it right here, the measure of CF. So the measure of CF, which is this guy right here, CF, this measure, well, if you look at the inscribed angle, because that's our intercepted arc here, the inscribed angle, that is 40, so CF would be a measure of 80. And then if we want to find the measure of angle, well, angle C here we have, angle C, we're looking for this angle. Well, that is an inscribed angle, and the intercepted arc is 98, so we're going to be half of 98, so the measure of angle C would be 49, and we're in degrees here as well. So that's how we can use this theorem. Key thing is going to be recognizing your inscribed angles and your intercepted arcs, and being able to use that relationship, because there'll be other relationships that exist, so it's about being able to recognize them. All right, our next and final theorem for the day, on page 724, it's theorem 10.7. It states that if two inscribed angles of a circle intercept the same arc or congruent arcs, then those two angles are going to be congruent. So I'll show you what they have written here and explain it to you. And if we have, here we go, this angle here and this angle here, can be a little tough to see, AD. So if we have, let's say, angle B is congruent to angle C, oh sorry, if angle B and angle C both intersect our AD here, if that's our intercepted arc for angle B and angle C, then angle B and angle C would be congruent if they both intersect the same arc. So since angle B, you know, DBA, that angle has arc AD, and also DCA is intercepting arc DA, therefore these angles would be congruent because they're intersecting the same arc. And you also could have the possibility of two arcs that are congruent, like let's say A, B, C, and then we have, try to draw my best here, angle D, E, F. If arc BC is congruent to arc EF, and they're both being intersected here, like angle A is intersecting arc BC, angle D is intersecting arc EF, if those two arcs are congruent, then these two angles will be congruent. That's what this theorem is stating. And we'll do a little example with this one, and then I'll give you some to try on your own, see if you recognize these relationships. So let's say we'll do the one in the book with a little bit of algebra here, incorporated in. There's our circle, and we have, actually we'll take the center away. So we have these two angles up here, angle at T and an angle at U, and we have S and V down here. That's going to be our arc. So we are given that we have 3x minus 5, that's the measurement for this angle, and we have 2x plus 15, and that would be for this angle. And I'm sure you can guess the equation we're going to make because of the theorem we just had. But because angle T is intersecting arc SV and angle U is also intersecting arc SV, they're going to be congruent to each other. So 2x plus 15 equals 3x minus 5. Bring your 2x over, add your 5, so x is equal to 20. And then if we want to find the measure of each angle, you would just substitute in. So 40 plus 15 is 55. That would be the measure of angle U. And hopefully the measure of angle T is the same because they should be congruent. 20 times 3 is 60, minus 5 is equal to our 55. The key thing here is going to be recognizing when you should use this theorem as opposed to using the past theorem or using other relationships that we will talk about in the future. So if you have two inscribed angles that intersect the same arc or congruent arcs, then they will have the relationship that they are congruent to one another. Go try some problems on your own. Have a nice day.